Look up at the night sky, and what do you see? A vast, glittering ocean of stars, each one a distant sun, some alone, others huddled together in tight-knit communities called star clusters. These cosmic gatherings are far more than just pretty arrangements of light. They're cosmic treasure chests, packed with secrets so strange they defy logic. Imagine a place where stars don't behave like they should, where ancient celestial bodies hold clues to the universe's darkest mysteries, and where astronomers keep uncovering phenomena that leave them scratching their heads. That's the world of star clusters, a place where the ordinary rules of space seem to break down. Some of these clusters are like celestial graveyards, hiding the remains of stars that died in violent, unexpected ways. Others are nurseries where newborn stars flicker to life under conditions that shouldn't exist. And then there are the rogue stars loners that dart through these clusters at impossible speeds, as if trying to escape something unseen. What's driving these bizarre behaviors? How do these clusters form in the first place? And why do some of them seem to defy the laws of physics? The answers might rewrite everything we think we know about the universe. In this journey, we'll uncover not one or two, but 30 of the strangest discoveries ever made about star clusters. We'll explore ghostly remnants of supernovas hiding in plain sight, stars that pulse with rhythms no one can explain, and mysterious gaps in clusters where stars seem to vanish without a trace. Some of these findings are so recent they haven't even made it into textbooks yet. Others have been hiding in old data for decades, waiting for someone to piece together the clues. By the time we're done, you'll never look at the night sky the same way again. So buckle up, we're diving deep into the cosmic unknown, where every discovery raises more questions than answers. The universe is stranger than we ever imagined, and star clusters are proof. In the heart of a dense star cluster called Messier 5, astronomers stumbled upon a cosmic predator, a pulsar dubbed the Black Widow, spinning at dizzying speeds while methodically destroying its stellar companion. This isn't science fiction, it's a real-life celestial crime scene unfolding in slow motion. The Black Widow earns its name from the way it feeds on its neighbor, blasting it with searing radiation and particle winds so intense they're literally stripping the star apart, atom by atom. Imagine a spider devouring its mate, but on a scale where the victim is a ball of gas thousands of miles wide. What makes this pulsar even more fascinating is how it betrays its presence. Using radio telescopes, scientists detected erratic flickers in the companion star's light, clues that something invisible but immensely powerful was tormenting it. The pulsar itself is a collapsed neutron star, only about 12 miles across but weighing more than our Sun, spinning hundreds of times every second. Each rotation sends out a beam of radiation that slices through space like a lighthouse from hell, cooking the nearby star and flinging its material into the void. Over thousands of years, this relentless assault will leave nothing behind but a ghostly trail of ionized gas. But here's the twist, this deadly dance might be more common than we ever realized. The Black Widow isn't alone. Similar systems have been spotted in other clusters, suggesting these cosmic killers could be lurking everywhere, rewriting the rules of stellar evolution. And every time we find one, it forces us to ask, how many stars in the night sky are actually hiding such violent secrets? The universe, it seems, has a dark side, and star clusters are where its most ruthless dramas play out. Deep within ancient star clusters, where most stars are aging giants or dim remnants, astronomers keep finding cosmic imposter stars that glow with the energetic blue light of youth, burning far brighter and hotter than they should. These are blue stragglers, the ultimate rule breakers of stellar evolution. Picture a retirement home where one resident inexplicably has the vitality of a 20-year-old while their peers show the wear of time. That's the mystery these stars present. They exist in clusters billions of years old, where every star should have grown red and dim long ago, yet there they shine defiant, vibrant, and utterly out of place. So what gives these stars their second wind? The leading theory is as dramatic as it sounds: stellar cannibalism. In the crowded cores of star clusters, where stars jostle for space like commuters in a cosmic subway, collisions aren't just possible, they're inevitable. When two aging stars crash together, their outer layers violently fuse, creating a single, reborn star with a fresh supply of hydrogen fuel. It's like tossing two half-burned logs into a fire combined. They blaze brighter than before. The result is a blue straggler, a star that looks rejuvenated because in a way it is. But these mergers aren't tidy affairs. Hubble Space Telescope observations have captured blue stragglers with odd chemical fingerprints, too much carbon, too little oxygen, hinting at the chaotic mixing of stellar guts during collisions. Some even show evidence of devouring a third star, like celestial leftovers from a messy cosmic meal. And in Globular Cluster M30, researchers found blue stragglers orbiting so close to other stars that they're likely locked in a slow-motion dance toward another merger. It's a stellar survival strategy: consume or be consumed. Yet not all blue stragglers fit this violent origin story. A handful appear isolated, too far from neighbors to blame a collision. This has led to a spine-tingling alternative. What if some steal fuel outright? Imagine a vampire star quietly siphoning hydrogen from a binary companion until it drains it dry. Telescopes have caught blue stragglers with faint, exhausted partners, stellar husks that once donated their lifeblood. Whether through crashes or theft, these stars cheat time itself, forcing us to rewrite the rules of how stars live, die, and sometimes refuse to fade away. Star clusters are supposed to follow a predictable life cycle: birth, maturity, and eventual fade into old age. But something strange is happening in their twilight years. Astronomers keep counting fewer red giant stars than the math says should be there. It's like walking into a retirement home and realizing half the residents vanished without explanation. Take the Globular Cluster M4, for example. Based on its age and the number of stars it contains, there should be hundreds of these swollen, aging stars glowing faintly in its core. Instead, surveys show barely half that amount. Where did they go? The answer might lie in the chaotic environments these stars call home. In the dense heart of a globular cluster, stellar traffic jams are constant. Stars don't just pass each other politely. They yank, twist, and sometimes violently eject one another through gravitational tug-of-wars. A red giant, bloated and fragile in its old age, is particularly vulnerable. One close encounter with a younger, more massive star could strip its outer layers or fling it into the void entirely. Hubble's observations of cluster NGC 6709 revealed trails of ionized gas potential crime, seen evidence of red giants being torn apart mid-evolution. But some researchers suspect an even darker force at play: invisible halos of dark matter. If certain clusters harbor more of this mysterious substance than we've accounted for, its gravitational grip could be disrupting stellar life cycles in ways we don't yet understand. In the cluster Omega Centauri, the distribution of missing red giants matches patterns that suggest an unseen structure, perhaps a hidden knot of dark matter altering the fate of these stars. It's a cosmic whodunit with two compelling suspects: brutal stellar interactions or the shadowy influence of the universe's most elusive material. The implications are staggering. If violent encounters are the culprit, it means star clusters are far more destructive neighborhoods than we thought. But if dark matter is interfering, these clusters could become unexpected laboratories for studying its secrets. Either way, the missing red giants are forcing astronomers to rethink how stars live, die, and sometimes disappear without a trace. Picture a cosmic slingshot, flinging stars across the galaxy at speeds so intense they could cross the length of the United States in less than a second. These aren't just fast-moving stars, they're hypervelocity runaways, stellar fugitives rocketing through space at over 1 million miles per hour. Their origins traced back to the gravitational chaos of star clusters. Take HD 271,791, a massive star hurtling through the Milky Way at nearly 2 million miles per hour. Its trajectory is so extreme that it's not just escaping its home cluster, it's on a one-way trip out of the galaxy entirely. How does a star reach such impossible speeds? The answer lies in the ferocious gravitational tug-of-war that plays out in dense star clusters. When a star drifts too close to a binary system, a pair of stars orbiting each other, the interplay of forces can become lethal. One star might get captured while the other gets violently ejected, catapulted outward like a stone from a sling. In some cases, the runaway star isn't just flung by its neighbors, it's launched by the supermassive black hole lurking at the center of the Milky Way. Observations of stars like S5 HVS1 show trajectories pointing straight back to the galactic core, as if they were spat out by an invisible cosmic cannon. But not all hypervelocity stars follow the rules. Some, like LP 4030-932, move so fast they shouldn't exist at all. Their speeds defy conventional models of gravitational ejection, hinting at even wilder origins, perhaps a close encounter with a rogue black hole or the explosive aftermath of a supernova. And then there's the curious case of white dwarfs like D66, racing through space with enough velocity to escape the Milky Way's gravitational pull entirely. These burned-out stellar cores are proof that even dying stars can become galactic outlaws. What happens to these runaway stars? Some tear through interstellar gas, leaving glowing shock waves in their wake like cosmic breadcrumbs. Others, stripped of their planetary systems during their violent ejection, drift alone through the void-frozen relics of the clusters that rejected them. But their journeys give us something priceless, a way to map the hidden forces shaping our galaxy. By tracing their paths backward, astronomers can reconstruct the gravitational battles that launched them, revealing secrets about the clusters and black holes they fled. The universe doesn't just create stars, sometimes it throws them into the dark like celestial dice, spinning tales of speed, survival, and escape. Among the countless star clusters scattered across the cosmos, one stands out not for what it shows, but for what it doesn't. Scientists call it a dark cluster, a gravitational ghost haunting the edges of our galaxy. Unlike typical clusters, which glitter with thousands of visible stars, this enigma reveals itself only through its pull on surrounding matter, like an invisible hand bending the fabric of space. The first hints emerged when astronomers noticed stars near the Milky Way's outskirts moving strangely, as if tugged by something massive. Yet when they pointed their telescopes toward the source, they found nothing but empty space. Could this be a failed star cluster, a place where stars tried to form but never ignited? One theory suggests it might be a cold, dense cloud of gas that collapsed under its own gravity, but without enough heat to spark nuclear fusion. Picture a cosmic dud, a fireworks shell that packed all the gunpowder but never lit. Alternatively, it might be the skeletal remains of a once vibrant cluster, its stars long since ripped away by galactic tides, leaving only their combined gravity behind like a fingerprint at a crime scene. Then there's the spine-tingling possibility, pure dark matter. If this cluster is held together not by stars but by the universe's most mysterious substance, it would be the first direct evidence of dark matter naturally clumping into structures akin to star clusters. Observations of similar gravitational anomalies in the Fornax galaxy hint that such invisible assemblies might be more common than we ever imagined, but proving it is another challenge entirely. Without visible stars to track, researchers must rely on subtle distortions in background starlight or the faintest whispers of X-rays emitted by trapped gas, clues so delicate they border on cosmic guesswork. The dark cluster forces us to confront a humbling truth. We might be missing entire chapters of the universe's story, hidden in plain sight. Whether it's a graveyard of failed stars or a shadowy knot of dark matter, its existence suggests the cosmos operates by rules we've only begun to glimpse. And if such invisible structures are out there, how many more are waiting to be found? Hidden in the ancient star cluster Messier 4, about 5,600 light-years from Earth, astronomers found something that defies even the wildest sci-fi fantasies, a planet made almost entirely of diamond. This isn't some glittering cosmic metaphor. It's a real, documented world where the crushing forces of gravity and extreme heat have compressed carbon into a crystalline structure the size of a planet. And it orbits not a normal star, but a pulsar, a rapidly spinning stellar corpse that blasts it with deadly radiation every few milliseconds. The story of this diamond planet's discovery reads like a cosmic detective novel. Astronomers were studying a pulsar named PSRB 1620-26 when they noticed something bizarre. Its regular radio pulses were occasionally arriving a fraction of a second early or late. That tiny irregularity was the clue. Something massive was tugging on the pulsar, warping space-time just enough to disrupt its rhythm. Further observations revealed the culprit, a planet about the size of Jupiter, but with a density so high it could only be one thing: carbon squeezed into diamond under pressures unimaginable on Earth. How does such a world even form? The leading theory is as dramatic as the planet itself. Picture a once normal star in a binary system orbiting alongside the pulsar. As the pulsar's intense radiation and gravitational forces tore into its companion, it stripped away layers of hydrogen and helium, leaving behind a naked core of oxygen and carbon. Under the pulsar's relentless pull, this core collapsed further, compressing the carbon into a crystalline lattice, a diamond forged in the heart of a stellar apocalypse. But the real shock came when scientists calculated the planet's composition. Based on its mass and orbit, they estimate it's composed of carbon so dense that a single sugar cube-sized chunk would weigh as much as a small car. Some models even suggest that beneath the diamond crust lies an ocean of liquid carbon, churning in perpetual darkness. The discovery rewrites what we thought possible for planets. Most worlds form from the leftovers of star birth, rich in silicates and metals. This one, though, is a relic of stellar destruction, a glittering gravestone marking where a star was torn apart and reborn as something utterly alien. And it raises an eerie question. If a diamond planet exists in Messier 4, how many more of these cosmic jewels are lurking in the dark, waiting to be found? The universe, it seems, has a taste for the extravagant, and star clusters are its treasure chests. In the ancient heart of Omega Centauri, a colossal star cluster floating 13,000 light-years away, astronomers have found celestial rebels that refuse to die, stars burning with a vigor that defies time itself. These aren't just old stars clinging to life. They're cosmic anomalies that appear to have cheated death multiple times over, glowing with the energy of stars half their age. One particular red giant, catalogued as V2, stands out like a flaming thumbprint in the cosmos. It pulses with a rhythm that suggests not just one lifetime of nuclear fusion, but possibly 2 or even 3. How does a star become immortal? The answer might lie in the chaotic dance of Omega Centauri's core, where stellar densities are so high that collisions aren't rare, they're inevitable. Picture two aging stars spiraling toward each other, their outer layers merging in a violent embrace. The resulting fusion doesn't just create a bigger star, it reignites the nuclear furnace at its core, effectively hitting the cosmic reset button. For a star on the brink of burning out, this collision is like a shot of adrenaline, a second wind written in fire and gravity. Spectroscopic data from these stars reveal bizarre chemical fingerprints with abnormal levels of lithium and carbon, elements that should have been consumed billions of years ago. It's as if these stars rummaged through the cosmic recycling bin, stitching together new fuel from the ashes of their past lives. But collisions alone might not explain the most extreme cases. Some researchers speculate these stars could be tapping into something far stranger: exotic matter. In the crushing pressures of Omega Centauri's core, where gravity warps space into knots, theoretical particles like strange quarks might form, altering how stars burn. A handful of these immortal stars exhibit energy outputs that don't match any known fusion process, flickering with rhythms that suggest internal engines unlike anything in our models. If confirmed, it would mean these stars aren't just surviving, they're rewriting the laws of physics to do it. The implications ripple far beyond one cluster. If stars can truly reboot themselves, it challenges our fundamental understanding of stellar life cycles. Galaxies might harbor far more ancient stars than we've accounted for, hidden in plain sight. And if exotic matter is involved, these cosmic elders could be our first glimpse into a shadow universe of particles and forces we've only dreamed of detecting. Omega Centauri's immortal stars aren't just curiosities, they're gatekeepers of secrets that could reshape our place in the cosmos. Star clusters should drift lazily through space, obeying the gentle tug of nearby galaxies, but some are racing toward an unseen finish line with unsettling urgency. Their trajectories point toward a patch of sky near the Hydra Centaurus supercluster, where something colossal lurks in the shadows. The Great Attractor, a gravitational anomaly so powerful it's pulling entire clusters toward it at over 600 miles per second. This isn't just distant speculation. Hubble's observations of globular clusters like NGC 6139 reveal stars moving in unison, as if swept up in a cosmic current no one can see. What makes this motion so eerie is that it defies the universe's grand expansion. Everything should be drifting apart, yet here are clusters, some over 100 million light-years away, all streaming toward the same invisible focal point. Astronomers call this coordinated drift dark flow, and it hints at structures so vast they bend the fabric of the cosmos itself. The Great Attractor might not even be the source. It could merely be the tip of something far larger, like a hidden supercluster of galaxies or a concentration of dark matter with the mass of tens of thousands of Milky Ways. The smoking gun lies in the cluster's peculiar velocities. Take the Norma cluster embedded within the Great Attractor's grip. Its stars don't just move, they accelerate, as if sliding down an invisible slope. Even stranger, some clusters exhibit motion that can't be traced to any known celestial body. Their paths suggest the influence of something beyond our observational horizon, a ghost mass warping space-time from realms we can't yet map. But here's where it gets truly bizarre. Some researchers propose this dark flow might be evidence of other universes, parallel cosmic domains whose gravity leaks into ours, tugging star clusters like puppets on invisible strings. While that remains speculative, one thing is clear. The Great Attractor connection proves we've barely scratched the surface of the universe's grand design. Every cluster caught in this mysterious flow is a breadcrumb leading us deeper into the unknown, where the rules of gravity and reality itself might rewrite before our eyes. And the Great Attractor isn't acting alone. Recent sky surveys suggest it's part of a larger conveyor belt called the Laniakea supercluster, a cosmic web where galaxies and star clusters flow like rivers toward a shared gravitational abyss. This isn't just about where clusters are going. It's a clue to where everything in our corner of the universe is destined to end up. The motions we're witnessing today might trace the blueprint of the universe's ultimate fate, written in the silent drift of ancient stars. Deep in the cosmic void's vast, empty regions where galaxies are scarce and star formation should be nearly impossible, Hubble's sharp eye caught something impossible. Brilliant blue knots of newborn stars blazing against the darkness like campfires in a desert. Astronomers call them blue blobs, and their very existence throws star formation theories into chaos. These clusters aren't just young, they're massive, each packing thousands of stars into tight spheres no wider than a few hundred light-years. The strangest part, they're floating alone in the abyss, far from the dense gas clouds or galactic collisions that usually trigger such stellar fireworks. Take the blue blob discovered in the Leo ring, a massive loop of gas drifting between galaxies. Here, in a region so empty it's been called a desert of the cosmos, Hubble spotted clusters with stars less than 100 million years old, infants by cosmic standards. Their vibrant blue hue betrays their youth, as only hot, massive stars burn that color. But without the gravity of a galaxy or the shockwaves of a collision to compress gas into stars, how did these clusters ignite? The leading theory is as fragile as it is fascinating. In these voids, subtle gravitational tugs might have stirred the sparse gas over eons, creating pockets dense enough to collapse under their own weight. It's like expecting a whisper to start an avalanche, yet somehow it worked. Even more baffling is their survival. Young, massive stars are notorious for blowing away their birth clouds with fierce stellar winds. In a void where replacement gas is scarce, these clusters should have strangled themselves within millions of years. Yet somehow they persist. Spectroscopic data reveals their gas reservoirs are oddly replenished, as if these stellar nurseries have found a way to recycle material against all odds. Some show faint filaments connecting them to distant gas streams, cosmic lifelines threading through the void. The implications rewrite the rules of star birth. If clusters can form in the universe's emptiest reaches, then the ingredients for stellar life are more versatile than we imagined. Perhaps voids aren't deserts at all, but stealthy incubators hiding star-forming potential in the quietest corners of space. Every blue blob we find is a clue challenging us to rethink where and how the cosmos chooses to ignite its lights, and with each discovery, the message grows clearer. The universe doesn't play by our rules. It writes its own. In the crowded stellar neighborhoods of star clusters, death doesn't always mean the end. Some stars refuse to fade quietly into the cosmic night, resurrecting as celestial zombies, stellar remnants that keep glowing through unknown means, violating every textbook model of stellar demise. Take LP 4365 in Messier 67, a star that should have died in a supernova explosion millions of years ago, but instead wanders the cluster like a radioactive ghost, pulsing with eerie regularity while trailing heavy elements normally forged in stellar explosions. What makes this zombie star so unsettling is its composition. Spectroscopic analysis reveals absurdly high concentrations of neon, magnesium, and calcium, elements typically scattered into space during a supernova. Yet here they are, bound within a still glowing fragment of the original star, as if the explosion got cold feet halfway through. The star's motion is equally bizarre. It's racing through the cluster at nearly 2 million miles per hour, an escape velocity suggesting it was violently ejected during whatever partial catastrophe it survived. The leading theory, LP 4365, might be the charred remains of a white dwarf that underwent a failed supernova, an explosion too weak to completely obliterate the star. Picture a bomb with a faulty detonator, blasting away half the structure but leaving the core eerily intact. Unlike normal white dwarfs, which cool into dark cinders over billions of years, this one maintains a bizarre afterglow, possibly heated by radioactive elements churned up during its botched death. Some astronomers speculate its pulsations come from internal G-forces warping its fractured structure, like a slowly deflating balloon with cosmic indigestion. But LP 4365 isn't alone. The Kepler Space Telescope has spotted similar zombie stars in other clusters, each with its own nightmarish quirks. One in the Globular cluster, NGC 6397, flickers like a candle in a draft, its brightness changing unpredictably, as if whatever energy source keeps it animate is running low or misfiring. Another, in the Open cluster, NGC 6791, shows spectral lines indicating it's wrapped in a shroud of its own ejected material, like a star wearing its own funeral shroud. These undead stars force us to confront glaring gaps in our understanding of stellar death. Supernova might not always be clean, all-or-nothing events. Some stars could fail catastrophically, leaving behind radioactive wreckage that stubbornly refuses to go dark. And if that's true, how many other cosmic zombies are lurking in plain sight, masquerading as normal stars while hiding their violent past? Even stranger, some models suggest these zombies might not be dead at all but reborn. A handful exhibit traces of fresh hydrogen in their atmospheres, hinting they might be cannibalizing nearby gas to reignite fusion in their cores. It's stellar vampirism on a cosmic scale, stars that cheat death by feeding on their surroundings. The universe, it seems, has a dark sense of humor, creating monsters that defy categorization, then scattering them through the star clusters we thought we understood. Every zombie star we find is a crack in the foundation of astrophysics, proving that even the most violent stellar deaths can have survivors. And as we keep searching, one question lingers: if stars can come back from the grave, what other cosmic rules might be ripe for rewriting? In the dense stellar crowds of the M5 globular cluster, astronomers found a cosmic pairing so bizarre it made them question decades of astrophysics. A neutron star and white dwarf whirling around each other at a distance that should be impossible. This isn't just a close orbit, it's a death-defying dance where the two stars complete a full loop every 26 minutes, closer than the Moon is to Earth. At that range, conventional models insist the white dwarf should have been torn apart by tidal forces or consumed by its dense companion eons ago. Yet here they are, locked in a gravitational embrace that defies every expectation. The discovery hinged on a tiny but telling clue: a rhythmic flicker in the neutron star's X-ray emissions. Like a cosmic metronome, the pulses arrived with clockwork precision, except for occasional minuscule delays. Those delays betrayed the presence of an unseen companion, its gravity warping space-time just enough to bend the neutron star's signal as it orbited. When researchers calculated the system's parameters, the numbers didn't add up. The white dwarf, a burned-out stellar core roughly the size of Earth but half the Sun's mass, was far too big to survive so close to a neutron star without being shredded. How did this system cheat destruction? The answer might lie in its violent past. Simulations suggest the white dwarf was once a red giant, its outer layers stripped away by the neutron star's gravity over billions of years. What remains is an ultra-dense core, packed so tightly that it resists tidal disruption, a stellar phoenix reduced to its barest, toughest form. But even that doesn't fully explain the orbit's stability. Some theorists propose the neutron star's magnetic field acts as an invisible shield, buffering the white dwarf from catastrophic forces. Others speculate the pair formed through a rare three-star interaction, where a chaotic gravitational shuffle left them in this improbable configuration. The implications ripple beyond one star cluster. If such tight binaries can exist, it means our models of stellar interactions are missing critical physics, perhaps a mechanism that allows stars to harden their orbits over time, resisting in-spiral. It also raises the tantalizing possibility of more extreme pairings: neutron stars orbiting so close they're practically touching, or white dwarfs skimming the surfaces of black holes. Every impossible binary we find is a reminder that the universe thrives on exceptions, rewriting the rules just when we think we've figured them out. And then there's the timing anomaly that started it all. Those delayed X-ray pulses aren't just a clue, they're a cosmic stopwatch, measuring relativistic effects with precision no earthly lab could match. As the white dwarf tugs at the neutron star, it creates subtle shifts in the pulse arrival times, allowing astronomers to map the system's gravity in exquisite detail. It's a natural laboratory for testing Einstein's theories, proving once again that star clusters aren't just collections of old stars. They're crucibles where the universe's strangest experiments unfold. Some star clusters seem to play by their own rules, and NGC 2808 is one of them. At first glance, it looks like any other globular cluster, a dense ball of ancient stars orbiting the Milky Way. But when astronomers trained their spectroscopes on its individual stars, they stumbled upon a cosmic anomaly. Instead of a uniform family of stars forged from the same primordial gas, NGC 2808 contained two distinct populations with wildly different chemical fingerprints. One group was rich in helium and nitrogen, while the other showed barely a trace. It was like finding two separate generations of stars packed into the same celestial apartment building, each with its own origin story. The discovery sent shockwaves through astrophysics because it challenged a fundamental assumption that globular clusters formed all at once from a single cloud of gas. Yet here was proof that some clusters had undergone multiple star-forming episodes, with a second wave igniting billions of years after the first. The helium-rich stars in NGC 2808 aren't just chemically distinct, they're hotter and bluer, burning fuel so fiercely that they stand out like flares against the cooler, older population. How did these two groups end up together? The leading theory involves a dramatic cosmic recycling program. When the cluster's first generation of massive stars died, they spewed helium-enriched material back into the cluster's core through supernova or stellar winds. Over eons, this polluted gas collapsed under gravity, birthing a new wave of stars with a completely different chemical recipe, but the real twist lies in the timing. For this second generation to form, the cluster must have held onto its gas for an unusually long time, something globular clusters aren't supposed to do. Most blow away their raw materials after the first burst of star formation, like a factory shutting down its assembly line. NGC 2808, however, somehow kept its gas trapped, possibly due to an unusually deep gravitational well or a fortuitous lack of disruptive supernova. The result is a stellar time capsule, preserving not one but two distinct chapters of star birth in the same cluster. Even stranger, these dual population clusters might be more common than we thought. Omega Centauri, another massive globular cluster, shows at least 5 distinct stellar groups, each with its own chemical signature. Some stars there are so rich in heavy elements that they resemble those found in the Milky Way's disk, suggesting the cluster could be the remnant core of a dwarf galaxy devoured long ago. The implications are staggering. If star clusters can harbor multiple generations, they might be far more dynamic and far less predictable than our textbooks ever suggested. What does this mean for our understanding of the early universe? These clusters could be holding clues about how galaxies assembled their first stars, or how matter recycled in the cosmos's youth. Every dual population cluster we find is a puzzle piece, hinting at a past where star formation wasn't a one-time event, but a messy stop-and-start process written in helium, hydrogen, and starlight. And if that's true, we might need to rethink not just how clusters form, but how entire galaxies grew up around them. Deep in the heart of star clusters, where stars pack together like commuters in a cosmic subway, astronomers are hunting for the source of one of space's most baffling signals: fast radio bursts. These millisecond-long blasts of radio waves, each unleashing more energy than the sun does in decades, have puzzled scientists since their discovery in 2007. But recent observations have traced some of these bursts back to an unlikely birthplace: dense star clusters, where violent stellar remnants called magnetars might be firing them into the void like interstellar lighthouses. Take the case of FRB 2000-2014, a burst that flickered from the direction of globular cluster M81. When researchers pinpointed its origin, they found something unexpected: not a distant galaxy, as most FRBs seem to originate, but a cluster of ancient stars right in our cosmic backyard. At the heart of that cluster lurks a magnetar, a neutron star with a magnetic field so strong it could strip the data from a credit card halfway across the solar system. Magnetars are known for their erratic outbursts, twisting magnetic fields until they snap like rubber bands, releasing catastrophic energy. But linking one directly to an FRB was a first, and it suggests these clusters could be hiding more of these cosmic radio cannons. What makes star clusters such perfect FRB factories? The answer lies in their extreme environments. In places like M81, where stars orbit mere light weeks apart, gravitational chaos reigns. Neutron stars collide, black holes merge, and magnetars get jostled like pinballs, any of which could trigger the conditions needed for an FRB. Some theorists propose that when a magnetar's crust cracks under magnetic strain, it creates a shock wave that accelerates particles to near light speed, generating a radio burst bright enough to be seen across the universe. Others suggest these bursts might come from magnetars tangled in debris disks, leftovers from torn-apart companion stars, wherein falling material triggers periodic eruptions. Yet not all FRBs fit this mold. Some repeat randomly, while others fire just once and vanish. The star-cluster connection might explain only a fraction of them, leaving the rest shrouded in mystery. And then there's the distance problem. Most known magnetars are in our galaxy, yet FRBs arrive from billions of light-years away. If star clusters are truly FRB hotspots, it implies ancient magnetars in far-off clusters are somehow more active or more unstable than their local counterparts. The implications stretch far beyond astrophysics. If magnetars in star clusters are indeed behind some FRBs, these bursts could become tools for probing the universe's structure. As FRB waves travel through space, they're distorted by the gas and plasma they pass through like a flashlight beam shining through fog. By studying these distortions, astronomers could map the invisible matter between galaxies. And if clusters are producing them, it means we've stumbled onto a natural cosmic beacon, flashing from the densest neighborhoods in existence. Every new FRB traced to a star cluster is another piece of the puzzle, hinting that these ancient stellar cities aren't just relics of the past, they're active, explosive laboratories where the universe's most extreme physics play out. And with each detection, we get closer to answering the bigger question. What else are these clusters hiding in their crowded, chaotic hearts? Star clusters are supposed to be organized chaos, millions of stars swirling in predictable patterns, bound by gravity's unbreakable rules. But scattered across these cosmic metropolises are celestial rebels, stars following orbits so steeply tilted, so wildly off-kilter, they shouldn't exist. Take the star labeled S2 in the NGC 6397 cluster, looping around the cluster's core at a jaw-dropping 80-degree incline, like a car driving vertically up a skyscraper instead of circling it. These aren't just odd paths, they're gravitational heresy, trajectories so unstable they should have collapsed into the cluster's heart eons ago. Yet here they are, tracing defiant circles in the sky as if thumbing their noses at physics. The mystery deepens when you calculate the forces at play. In a crowded cluster core, stars whip past each other at blistering speeds, their collective gravity acting like cosmic traffic cops, usually keeping orbits neatly aligned. For a star to maintain a steeply inclined orbit, something unseen must be shielding it from this gravitational tug-of-war. The prime suspect, an invisible anchor, an intermediate mass black hole lurking undetected at the cluster's center. These elusive objects, weighing between 100 and 100,000 suns, would pack enough gravitational punch to shepherd stars onto bizarre paths without being directly visible. Observations of the globular cluster Omega Centauri support this idea. There, stars near the core show erratic motions consistent with an invisible mass roughly 40,000 times that of our Sun, a black hole large enough to bend the rules but small enough to evade detection. Yet black holes aren't the only explanation. Some simulations suggest these unnatural orbits could be scars from the cluster's violent youth, perhaps a close encounter with another cluster or galaxy that jostled stars onto new trajectories like billiard balls struck mid-game. In the case of Messier 15, astronomers found stars with retrograde orbits moving backward relative to the cluster's rotation, a smoking gun for some ancient gravitational hijacking. Others propose these stars might be interlopers, captured from passing dwarf galaxies and flung into odd angles by the cluster's spin, the most tantalizing clue comes from the orbits themselves. Many of these tilted paths are rosettes, complex loops where a star's closest approach to the core shifts slightly with each revolution. General relativity predicts such patterns near massive objects where space-time warps like a twisted sheet. If these rosettes trace back to a single point, they could lead us straight to the hidden engine driving the chaos, whether that's a black hole, a dense knot of dark matter, or something even stranger. Every gravity-defying orbit we find forces us to reconsider what star clusters truly are. Not just serene retirement homes for ancient stars, but dynamic arenas where invisible players, black holes, dark matter, or gravitational echoes of past collisions still pull the strings. And with each tilted star we catalogue, the message grows clearer. The universe delights in breaking its own rules, leaving us to piece together the clues. The only certainty, wherever these cosmic rebels roam, the story is far from over. Westerlund 1 isn't just another star cluster, it's a cosmic titan, a sprawling stellar metropolis so massive it shouldn't exist. Nestled about 12,000 light-years away in the constellation Aura, this monster cluster packs hundreds of thousands of stars into a space only 6 light-years across. To put that into perspective, if our solar system were dropped into Westerlund 1's core, the night sky would blaze with stars so close they'd outshine the full moon by 100 times. But it's not just the density that baffles astronomers, it's the sheer scale. Most star clusters cap out at a few thousand stars. Westerlund 1 dwarfs them all, flaunting a population rivaling small galaxies. What makes this cluster truly extraordinary are its inhabitant stellar extremes that push the limits of physics. At its heart lurks Westerlund 1-26, a hypergiant so colossal it could swallow our Sun 1,000 times over. This star isn't just big, it's violent, erupting with enough energy in a single hour to power human civilization for 1,000,000 years. Nearby, a magnetar, a neutron star with a magnetic field a quadrillion times stronger than Earth's, spins furiously, its surface cracked by forces so intense they warp the fabric of space-time. These aren't just oddballs, they're relics of a chaotic birth that defies modern astrophysics. The problem, no current model can explain how Westerlund 1 formed. Clusters this dense usually unravel within a few million years, torn apart by the very stars they birth. Yet here it stands, stubbornly intact after 5 million years. One theory suggests it was born from the collision of 2 giant molecular clouds, a crash so violent it triggered a frenzy of star formation. Others speculate it might be the remnant core of a dwarf galaxy stripped bare by the Milky Way's gravity. But the most tantalizing clue lies in its star's composition, unusually high levels of heavy elements, hinting at a past drenched in supernova explosions. Could Westerlund 1 be the product of a chain reaction where dying stars seeded new ones in a self-sustaining cycle? The implications are staggering. If clusters like this can form and survive, they might be the universe's secret factories for forging extreme stellar objects. Black holes, magnetars, and hypergiants could all be more common than we thought, hidden in similarly overcrowded cosmic neighborhoods. And if Westerlund 1 is any indication, we've only scratched the surface of what's lurking in the densest corners of space where the rules of star formation aren't just bent but shattered. Hidden in the ancient star cluster 47 Tucani, something extraordinary lurks, stars with the chemical fingerprints of the universe's very first generation. These cosmic time capsules, discovered only in the past decade, carry traces of elements forged in the fiery hearts of stars that died over 13 billion years ago. Unlike normal stars, which are peppered with heavier elements like carbon and iron, these relics are bizarrely pure, almost entirely hydrogen and helium, with just a whisper of heavier material. It's as if they were brewed from the primordial soup of the Big Bang itself, untouched by the pollution of later stellar generations. This discovery is like finding a living dinosaur among modern birds. The first stars, known as Population 3, were theoretical giants hundreds of times more massive than the Sun, burning hot and fast before exploding in violent supernova. None have ever been directly observed, their light lost to time. But in 47 Tucani, astronomers spotted something unexpected: stars with minuscule amounts of strontium and barium, elements that could only have been sprinkled into their gas by those primordial supernova. These missing link stars aren't population 3 themselves, they're their descendants, carrying echoes of the universe's first nuclear furnaces in their atmospheres. How did these relics survive in a cluster that's otherwise rich in heavier elements? The answer might lie in 47 Tucani's chaotic youth. Early in its life, the cluster likely cannibalized a smaller, more pristine neighbor, a dwarf galaxy that had somehow avoided multiple generations of star formation. When the two merged, the pure stars from the dwarf were scattered like seeds into the cluster's outskirts, where they've persisted for billions of years, untouched by the pollution of later supernova. Observations from the Very Large Telescope in Chile revealed their hiding places: faint, red stars lingering on the cluster's fringes, their unusual chemistry betraying their alien origins. But here's the real shock: these stars aren't just oddities. They're a window into the universe's first moments. The precise ratios of their trace elements match predictions of how population 3 stars would have exploded, not in symmetrical supernova, but in asymmetrical, sloshing detonations that flung heavy elements in uneven bursts. That slight imbalance left patches of nearly pure gas amid the pollution, which later collapsed into stars like those in 47 Tucani. It's the first tangible evidence of how those first stars died and how they seeded the cosmos with the building blocks of everything that followed. The implications stretch far beyond one cluster. If these missing link stars exist here, they're likely hiding in others, perhaps even in our own galactic neighborhood. Finding more could help us piece together the full story of cosmic dawn, revealing how the first stars shaped the universe we see today, and that story is still being written. Every relic star we uncover is another clue, whispering secrets from an era when the universe was young, dark, and filled with giants. In the quiet depths of star clusters, astronomers keep finding something they can't explain: phantom X-rays flickering from empty patches of space. These aren't just faint signals. Some pour out enough energy to outshine entire galaxies, yet when telescopes swing toward the source, they find nothing. No stars, no black holes, just empty space crackling with invisible power. One of the most baffling cases comes from the Globular cluster NGC 6397, where the Chandra X-ray Observatory detected a source so bright it should have been visible to optical telescopes. But follow-up observations revealed only darkness, as if the X-rays were being broadcast by an invisible hand. What could possibly produce such intense radiation without leaving a trace? The leading suspect is a type of neutron star so dense and magnetic it bends light around itself like a cosmic cloaking device. These hidden pulsars might spin at blinding speeds, their beams of X-rays only visible when pointed directly at Earth, like a lighthouse whose rotating beam we catch in fleeting flashes. Others theorize these phantoms could be black holes too small to detect optically, their X-rays flaring as they shred passing gas clouds or even other stars. But the real curveball: some of these sources flicker with patterns that don't match any known celestial object. In the cluster M22, one X-ray phantom pulses erratically, its bursts arriving with no discernible rhythm, behavior unlike anything in the neutron star or black hole playbook. Then there's the distance problem. A handful of these phantom sources emit X-rays so intense that, based on their brightness, they should be located far outside the clusters. Yet their motion matches the cluster's own, proving they're bound to them gravitationally. This has led to a spine-tingling hypothesis. What if these are the first hints of quark stars? These theoretical objects, denser than neutron stars but not quite black holes, would consist of free quarks, the fundamental particles normally locked inside protons and neutrons. If they exist, their unique physics could explain both the extreme X-ray output and their invisibility to optical scopes. But the plot thickens. Some phantom sources vanish entirely after a few years, only to reappear decades later in the same spot. This behavior has no precedent in astrophysics. One explanation is that they're not single objects at all, but the aftermath of rare stellar collisions, cataclysmic mergers that leave behind short-lived X-ray fireballs. Others speculate they might be indirect evidence of dark matter interactions, with invisible particles annihilating each other and releasing bursts of energy detectable only in X-rays. Every unexplained source forces astronomers to confront the limits of our cosmic knowledge. Are these ghosts in the machine artifacts of instrumentation or rare alignments, or something far stranger? With each new phantom uncovered, the message grows clearer. Star clusters aren't just collections of aging suns. They're cosmic haunted houses where the rules of physics as we know them might not apply, and where the universe's next great mystery could be hiding in plain sight. Star clusters aren't supposed to break the rules, but in the ancient galaxy NGC 1268, astronomers found something that defies cosmic logic. A sparkling young cluster nestled among elderly stars, like a kindergarten classroom in the middle of a retirement home. This cluster, catalogued as NGC 1268-A, burns bright with blue-white stars no older than 50 million years, while the galaxy around it stopped forming new stars over 10 billion years ago. It's a glaring contradiction, a cosmic impossibility that shouldn't exist, and yet there it shines. How does a cluster stay young in a galaxy that's effectively dead? The leading theory is as audacious as it sounds: stellar rejuvenation through cosmic theft. Picture an aging star cluster drifting through the galaxy, its original gas long since blown away. Then, by chance, it plows into a lingering cloud of hydrogen, untouched since the galaxy's fiery youth. Like a vampire tapping an unexpected blood supply, the cluster greedily absorbs this fresh fuel, triggering a new round of star formation amidst its ancient members. Hubble's observations of similar clusters reveal telltale signs: young, blue stars wrapped in faint cocoons of gas, the smoking gun of recent stellar rebirth. But there's a catch. For this rejuvenation to work, the cluster must be massive enough to hold captured gas against the galaxy's tidal forces, and that's where things get stranger. In the galaxy M85, researchers found a young cluster weighing nearly 10 million suns, so dense it could trap gas even in a galaxy stripped bare of star-forming material. Its core houses bizarre hybrid stars, old red giants wrapped in newborn stellar disks, like grizzled warriors wearing the armor of youth. Spectroscopy shows these stars are chemically distinct from their surroundings, proof they formed from stolen gas rather than the galaxy's original supply. The implications ripple far beyond a few oddball clusters. If this process is common, it means galaxies we thought were dead might still be capable of spawning new stars under the right conditions. Some astronomers now suspect entire rogue populations of young stars could be hiding in plain sight, masquerading as ancient objects while secretly harboring youthful hearts. Even more intriguing, these clusters might be cosmic time capsules, preserving pockets of pristine gas from the early universe, untouched until a chance encounter reignited their stellar furnaces. Yet not all young in old clusters fit the theft narrative. A handful, like the one in elliptical galaxy NGC 4125, show no trace of captured gas. Instead, their youth might stem from a different kind of cosmic rebellion: collisions between white dwarfs or neutron stars, violent mergers that forge new stars from the ashes of dead ones. It's stellar alchemy of the highest order, turning stellar corpses into something vibrant and new. These age-defying clusters force us to reconsider how galaxies evolve and what dead really means in cosmic terms. Far from being static graveyards, ancient galaxies might harbor secret pockets of vitality, where clusters cheat time through ingenuity and sheer gravitational will. Every young cluster found in an old galaxy is a clue, hinting that the universe still has tricks up its sleeve and that the story of star formation is far from over. Globular clusters should be cosmic relics, ancient, predictable, and fading quietly into the universe's background. But when astronomers tallied them up, the numbers didn't make sense. Across galaxies, from spirals like the Milky Way to ellipticals 100 times its size, the count and arrangement of these dense star swarms defy every model we've built. This is the globular cluster problem, a puzzle so stubborn it's forced scientists to reconsider how galaxies form and what might be missing from our cosmic equations. Take the Milky Way as the first clue. Our galaxy hosts around 150 globular clusters, most orbiting the galactic halo in a loose spherical cloud. That seems reasonable until you compare it to massive ellipticals like M87, which boasts thousands of them. Scaling up a galaxy's mass should increase its cluster count, sure, but not by this staggering margin. Even stranger, some dwarf galaxies, barely 1% the Milky Way size, pack disproportionately large globular populations. The Fornax dwarf, for instance, holds 6 clusters despite its diminutive stature, as if it hoarded them like cosmic treasure. The plot thickens when you map their locations. In many galaxies, globular clusters split into 2 distinct families. One group orbits close to the core, rich in heavier elements like iron, evidence they formed from gas polluted by generations of supernova. The other group lingers farther out, chemically pristine, as if they've avoided the galaxy's pollution entirely. This duality suggests 2 separate origins, but current models struggle to explain how both populations could coexist in such starkly different environments. One radical theory proposes that many globular clusters weren't born in their current galaxies at all. They are cosmic hitchhikers, snatched up during galactic collisions. When the Milky Way devoured the Gaia-Enceladus dwarf galaxy 9 billion years ago, it may have absorbed dozens of clusters in the process. That could explain why some orbit backward or at odd angles, like strangers in a crowd. Yet even this can't account for the sheer excess in galaxies like M87, where the math suggests mergers alone couldn't have supplied so many. Then there's the dark matter complication. Simulations show that globular clusters should trace the distribution of a galaxy's dark matter halo, but in reality, they often cluster in ways that ignore this invisible scaffolding entirely. Some galaxies even have orphan globulars drifting far beyond where their dark matter halos should end, like kids who have wandered off the playground. The most tantalizing clue lies in their ages. Globular clusters are nearly as old as the universe itself, many dating back over 12 billion years. If they formed during the chaotic early universe, their survival and spread might reflect conditions we can't replicate in simulations. Perhaps a time when dark matter behaved differently, or when galaxy formation followed rules we've yet to decipher. Every unexplained cluster is a breadcrumb leading back to the universe's infancy, hinting that our models of cosmic evolution are missing a critical piece. Whether it's unseen physics, lost galaxies, or something even stranger, the globular cluster problem isn't just a gap in our knowledge. It's a window into everything we still don't understand about how the cosmos builds its structures. And until we solve it, we're left with a sky full of ancient star clusters that refuse to follow the script. Star clusters should be orderly places, with stars following predictable paths unless an invisible predator is lurking in their midst. Astronomers have detected telltale signs of rogue black holes drifting through these dense stellar communities, their presence betrayed only by the gravitational chaos they leave behind. In the globular cluster NGC 3200, researchers tracked a group of stars whipping around an empty point in space, their orbits suggesting the pull of something 4,000 times more massive than our Sun. Yet when telescopes scanned the area, they found nothing. No light, no X-rays, just empty space hiding a monster. How does a black hole end up roaming free in a star cluster? The answer lies in the violent dynamics of these crowded neighborhoods. When massive stars die, they can collapse into black holes. Normally, these sink to the cluster's core, but in rare cases, a gravitational slingshot, often from a close encounter with another black hole or a dense group of stars, can send one careening into the outskirts. Some might even get ejected entirely, becoming lone wanderers in the galactic void. The ones that stay behind, like the one in NGC 3200, lurk unseen, their darkness making them nearly impossible to spot unless they distort the motion of nearby stars or occasionally feast on a passing gas cloud. Finding these phantoms requires ingenious detective work. In the cluster M22, astronomers noticed stars accelerating inexplicably, their paths bending as if tugged by an unseen hand. By mapping these deviations, they reconstructed the presence of multiple black holes, each between 5 and 20 solar masses, drifting like ghosts through the stellar crowd. Even more chilling, some clusters might harbor dozens of these rogues, their combined gravity subtly warping the orbits of thousands of stars. The real mystery is why we don't see more of them. Current models predict that dense clusters should retain hundreds of black holes, yet confirmed detections remain rare. One theory suggests that most get evicted early in a cluster's life, flung out by gravitational pinball games during the chaos of youth. Others might cloak themselves in darkness, only revealing their presence when they rip apart a star or collide with another black hole, sending ripples through space-time. These rogue black holes aren't just cosmic oddities, they're potential keys to understanding some of the universe's biggest puzzles. Their movements could map the invisible distribution of dark matter in clusters, and their mergers might explain mysterious gravitational wave signals detected here on Earth. Yet for every one we find, countless others likely remain hidden, silent witnesses to the violence that shapes star clusters from within. And if their numbers are greater than we've dared to guess, they could rewrite what we know about how black holes form, evolve, and roam the cosmos. In the shadowy corners of star clusters, astronomers have stumbled upon a radical possibility: stars that don't burn like the others. These aren't your typical fusion-powered suns. They might run on something far more exotic: dark matter. Dubbed dark stars, these theoretical objects could rewrite the rules of stellar physics, glowing not from nuclear reactions but from the annihilation of invisible particles that make up the universe's most mysterious substance. The idea first gained traction when researchers noticed oddities in some of the universe's earliest star clusters. A handful of stars appeared too large, too bright, and too cold to fit standard models, like cosmic giants that somehow burn for billions of years without consuming their fuel. Simulations revealed a spine-tingling alternative. If dark matter clustered densely enough in the early universe, it could have fueled stars directly. As these hypothetical particles collided and annihilated within a star's core, they'd release energy not as a searing nuclear inferno, but as a steady, eerie glow radiating from within. What would a dark star look like? Picture a celestial body up to 1,000 times wider than our sun, yet surprisingly cool at its surface, more like a dim, red ember than a blazing fireball. Unlike fusion-powered stars, which stabilize by balancing gravity's inward pull with the outward pressure of nuclear reactions, dark stars would rely on the constant combustion of dark matter particles. Their lifespans could stretch for eons, outlasting normal stars by orders of magnitude, as long as their dark matter fuel held out. Evidence for these phantom stars remains elusive, but tantalizing clues exist. In globular clusters like Messier 13, certain red giants exhibit chemical signatures that don't quite match fusion-based evolution. Their atmospheres contain unexpected ratios of heavy elements oddities that could hint at a dark matter influence altering their internal engines. Even more provocative are observations of ultra-faint dwarf galaxies, where stars seem to shine far longer than their meager hydrogen supplies should allow, as if propped up by an unseen energy source. Critics argue that dark stars remain speculative, a fascinating what-if without definitive proof. After all, dark matter itself has never been directly detected, let alone observed powering a star. Yet proponents counter that their existence would solve multiple cosmic puzzles, from the unusual brightness of some early galaxies to the surprising abundance of hydrogen in the ancient universe. If dark stars formed before conventional ones, they could have acted as cosmic lighthouses, illuminating the universe's dark ages and seeding the first heavy elements in ways we're only beginning to unravel. The hunt for these shadowy giants is heating up. Next-generation telescopes like the James Webb Space Telescope are scouring ancient star clusters for infrared signatures that might betray a dark star's presence. Cool, massive objects radiating just enough heat to stand out against the cosmic background. Meanwhile, particle detectors on Earth keep searching for the dark matter particles that could make such stars possible, linking the invisible fabric of the cosmos to the very engines of starlight. Whether dark stars are real or not, their mere possibility forces us to confront how little we truly understand about the universe's hidden scaffolding. If they exist, they'd be living relics of a time when dark matter wasn't just an invisible halo around galaxies, it was the fuel that lit the first fires in the cosmic dark. And if they don't, well, the universe has surprised us before. Every odd star, every unexplained glow, is a reminder that the rules we've written for the cosmos might just be the first draft of a much stranger story. Palomar 5 isn't just a star cluster, it's a cosmic crime scene slowly unraveling in real time. Stretching across the Milky Way's halo, this ancient globular cluster is being methodically torn apart by our galaxy's gravity, leaving behind a glittering trail of stars like breadcrumbs in the dark. What makes Palomar 5 so special isn't just its fate, but how it's revealing the brutal mechanics behind how star clusters die. Most clusters fade quietly, their stars drifting apart over eons. But Palomar 5 is putting on a show, its destruction painting a roadmap of tidal forces that might explain the ghostly stellar streams weaving through our galaxy. The first clue something was unusual came when astronomers noticed Palomar 5 stars weren't neatly contained. Instead, they formed two enormous tails stretching over 30,000 light-years, one ahead of the cluster's orbit, the other trailing behind. These aren't just random scatterings, they're the fingerprints of gravitational torture. As the cluster swings around the Milky Way, our galaxy's tides pull harder on the near side than the far side, stretching the cluster like taffy. Stars at the edges get peeled away, forming streams that trace the cluster's orbital path. The process is relentless. Estimates suggest Palomar 5 has already lost 2/3 of its original mass, and within 100 million years, a blink in cosmic time it'll be gone entirely, dissolved into the Milky Way's halo. Yet these streams are more than just debris. They're celestial seismographs recording the Milky Way's gravitational tremors in exquisite detail. By mapping their twists and gaps, researchers have uncovered invisible structures, dark matter clumps, rogue black holes, even dwarf galaxies that have yanked on the streams over time. One particularly jagged kink in Palomar 5's tail points to a recent brush with the Milky Way's Sagittarius dwarf galaxy, proving these streams can serve as cosmic collision detectors. But here's the twist: Palomar 5 might not be the victim here, but an accomplice in its own destruction. Unlike typical globular clusters, which pack hundreds of thousands of stars into tight spheres, Palomar 5 is strangely fluffy, its stars spread so thin that the cluster's own gravity struggles to hold them together. This loose structure makes it especially vulnerable to tidal forces. Some astronomers speculate it was born this way, a fragile oddball among clusters. Others argue it was once denser, but repeated passes through the Milky Way's disk have whittled it down over billions of years. Either way, its flimsiness is accelerating its demise, offering a preview of what could happen to other clusters in the distant future. The most startling revelation: Palomar 5 streams might be hiding a secret population of black holes. Recent simulations suggest up to a third of the cluster's mass could be invisible stellar remnants, their gravity helping sculpt the stream's unique filamentary structure. If true, it would mean we're not just watching a cluster die, we're seeing how black holes redistribute themselves into galactic halos, seeding future gravitational waves and mergers. Palomar 5's destruction is a reminder that star clusters aren't eternal. They're transient sculptures shaped and eventually erased by forces far beyond their control. But in their death throes, they give us something priceless. A front-row seat to the invisible forces shaping our galaxy, written in the language of escaping stars. And as astronomers study its unraveling threads, they're piecing together a story that doesn't end with Palomar 5, because where one cluster fades, others are already leaving their own trails in the dark. Star clusters are supposed to be time capsules, preserving the chemical makeup of the early universe, so when astronomers found metal-rich stars in ancient globular clusters, it sparked a cosmic scandal. These clusters, like NGC 6535, contain stars with iron levels 10 times higher than expected for their age, as if someone dumped industrial waste into a prehistoric forest. The discovery throws a wrench into decades of stellar evolution models, forcing scientists to reconsider how quickly the universe's first heavy elements spread and what hidden forces might have jump-started cosmic chemistry long before we thought possible. The puzzle starts with stellar generations. After the Big Bang, the universe contained only hydrogen, helium, and trace lithium. Heavier elements like iron formed later, forged in supernova or neutron star collisions and scattered across space to seed new stars. Globular clusters born in the cosmos's infancy should reflect this, their oldest stars pristine, their younger ones slightly polluted by later generations of explosions. Yet in clusters like Omega Centauri, metal-rich stars appear alongside metal-poor ones with no clear evolutionary link, like finding a stainless steel skyscraper in a Bronze Age village. How did these metals arrive so early? One radical theory suggests the first supernova were far more efficient at dispersing heavy elements than we'd imagined, their shock waves reaching neighboring star-forming regions at unprecedented speeds. Observations of the cluster NGC 2808 support this. Its metal-rich stars show oddly uniform iron levels, as if they formed from gas suddenly and uniformly enriched by a nearby catastrophe. Another possibility is that these clusters cannibalized smaller, metal-rich dwarf galaxies, absorbing their chemically advanced stars like cosmic thieves. The odd kinematics of some metal-rich stars orbiting backward or at steep inclinations hint at such violent acquisitions, but the most tantalizing clue comes from the metals themselves. In 47 Tucanae, certain stars contain abnormal ratios of europium to iron, a signature typically tied to neutron star mergers. If these collisions happened shockingly early, they could have peppered nearby gas clouds with heavy elements before most globular clusters finished forming. It's a cosmic plot twist. The very events we thought were rare in the early universe might have been commonplace, rewriting the timeline of chemical enrichment. The implications ripple far beyond star clusters. If metals spread faster than models predict, it means the universe's first planets and potentially life could have arisen billions of years earlier than we imagined. Ancient star clusters might hold the evidence, their metal-rich stars standing as monuments to a forgotten era when the cosmos learned to build complexity from chaos. And with every new cluster we analyze, the story grows richer, proving that even the oldest corners of space still have secrets to spill. Star clusters were long thought to be one-and-done factories, forming their stars in a single burst before fading into cosmic retirement. But scattered across the universe, astronomers are finding celestial phoenixes clusters that somehow rise from their own ashes to birth new generations of stars millions or even billions of years after their initial formation. Take the cluster NGC 2100, where Hubble spotted a population of baby stars sparkling amid ancient stellar relics, their blue brilliance defying the cluster's advanced age. These second-generation stars shouldn't exist, yet there they burn, proof that some clusters have cracked the code of cosmic rebirth. The secret lies in recycling on an astronomical scale. When massive stars in a cluster die, they don't just vanish. They explode, seeding their surroundings with heavy elements and shock waves that can compress nearby gas. Normally, this material would drift away, but in dense clusters like the Orion Nebula's trapezium group, gravity can trap the debris, creating fresh fuel for new stars. Infrared telescopes have caught this process in action, revealing tendrils of gas, rich in carbon, oxygen, and iron, wrapping around older stars like cosmic compost waiting to ignite. What makes this cycle truly remarkable is the timescale. In the Large Magellanic Cloud, the cluster NGC 1866 shows two distinct stellar generations separated by a staggering 50 million years, a gap that suggests these clusters can hold onto their gas for improbably long periods. Spectroscopy reveals the younger stars are chemically enriched, carrying the fingerprints of their predecessors' deaths in their atmospheres. It's stellar reincarnation written in neon and magnesium, the ashes of dead stars fueling new ones in an endless loop. Yet the rebirth process isn't always peaceful. Some clusters, like Westerlund 1, showcase violent stellar collisions as a catalyst for new star formation. When two aging stars smash together, the resulting shockwaves can trigger the collapse of nearby gas clouds, like kicking a cosmic beehive into activity. The result, baby stars forming in the wreckage of their elders, their births heralded by X-ray flares and swirling debris disks. The implications rewrite our understanding of stellar nurseries. If clusters can reactivate their star-forming engines, it means the universe's most fertile regions might be hiding in plain sight, not just in pristine gas clouds, but in the graveyards of dead stars. Every reborn cluster we find is a testament to the cosmos's thriftiness, proving that in space, nothing truly goes to waste, not even stardust. At the heart of the Carina Nebula, a cosmic nursery teeming with newborn stars, there's a cluster that shouldn't burn this bright. Inside the chaotic stellar sprawl of Trumpler 14, astronomers found stars radiating temperatures that defy every model of stellar infancy, blue-white infernos 10 times hotter than our Sun, with surface temperatures soaring past 100,000 degrees. These aren't just young stars, they're celestial blowtorches, scorching their surroundings with an intensity that leaves scientists baffled. The puzzle isn't just their heat, it's how they sustain it without self-destructing under the sheer force of their own energy. Normally, young stars heat up as they contract under gravity, but these outliers blast through expected thermal limits like cosmic overachievers. One theory points to radiation feedback, a runaway effect where the star's own ultraviolet light ionizes nearby gas, creating a pressure cooker of energy that loops back to superheat their outer layers. It's like a campfire doused with gasoline, with each photon stoking the flames higher. Hubble's ultraviolet observations of Trumpler 14 reveal halos of ionized hydrogen around these stars, their shimmering shells betraying the brutal feedback cycle at work. But radiation alone can't explain the most extreme cases. In the cluster Westerlund 2, some stars exhibit bizarre magnetic signatures, fields so tangled and intense they act like invisible furnaces, trapping and redirecting heat toward the surface. Imagine a star with its own internal heat ducts, forcibly channeling energy outward instead of letting it radiate evenly. These magnetic monsters might owe their freakish temperatures to turbulent births, where chaotic collapses during formation left their magnetic fields knotted like tangled phone cords, amplifying their thermal output through sheer cosmic friction. The real curveball comes from their longevity. Stars this hot should burn out fast, exhausting their fuel in a few million years. Yet in clusters like NGC 3060, these blue-hot anomalies persist alongside cooler siblings, hinting at hidden mechanisms that let them cheat stellar thermodynamics. Some researchers speculate they're tapping into deeper reserves of deuterium, a heavy hydrogen isotope that burns hotter and longer, while others argue they might be stellar mergers, their extra heat the lingering shockwaves of a violent collision. Then there's the environmental impact. These scorching stars don't just burn bright, they reshape entire clusters. Their blistering radiation strips atmospheres from nearby planets before they can form, and their stellar winds carve cavities in surrounding gas clouds, altering the birthplaces of future stars. In the Tarantula Nebula, one such hothead has hollowed out a bubble 60 light-years wide, its fury literally pushing the boundaries of its stellar neighborhood. What's clear is that these clusters are rewriting the rules of stellar adolescence. They're cosmic laboratories where stars don't just grow up, they rage against the limits of physics itself, burning hotter, brighter, and stranger than we ever thought possible. And with every new discovery, we're forced to confront an electrifying truth. The universe doesn't just make stars, sometimes it makes monsters. Not all stars stay where they're born. Drifting through the lonely stretches between clusters, astronomers have found celestial runaway stars with chemical tattoos that betray their violent past. These orphaned stars didn't form in isolation. They were flung from their homes by gravitational chaos, their compositions telling stories of collisions, near misses, and cosmic ejections too brutal to imagine. Take the star He 1327, discovered wandering the Milky Way's halo. At first glance, it looked like any other aging giant until spectrographs revealed its secret, a bizarre cocktail of elements, including unnaturally high levels of oxygen and neon. These aren't the elements a star makes on its own. They're the scars of a violent exit, likely forged in the heart of a globular cluster before being hurled into the void. The chemistry points to a specific trauma, a close encounter with a black hole or a neutron star, whose gravitational kick launched it like a slingshot at speeds over 1 million miles per hour. But the real smoking gun lies in their motion. These orphans don't drift aimlessly. Their trajectories trace backward to known clusters like cosmic breadcrumbs. One star, catalogued as J1923, zooms through space with such velocity that its path leads directly to the heart of Omega Centauri, as if it fled the cluster in a desperate escape. Simulations suggest it was likely ejected during a deadly game of gravitational pinball, perhaps a three-star interaction where two stars paired up and the third got tossed aside like collateral damage. The most haunting orphans, though, are the ones with no home to return to. In the Large Magellanic Cloud, researchers found stars rich in alpha elements magnesium, silicon, calcium, but lacking the heavier iron typical of their supposed siblings. These chemical misfits hint at an even darker origin. They might be survivors of clusters that no longer exist, their parent systems ripped apart by galactic tides billions of years ago. Their compositions are time capsules, preserving the chemical makeup of star clusters that vanished before Earth even formed. Yet these stellar outcasts aren't just relics, they're informants. By studying their speeds and compositions, astronomers can map the hidden forces shaping clusters from within. Some orphans carry traces of lithium, an element usually destroyed early in a star's life. Its presence suggests they were ejected before their host clusters could strip it away, freezing their chemical clocks at the moment of their escape. Others show odd carbon-to-nitrogen ratios, evidence they were torn from binary systems where they'd been siphoning material from a companion. Every orphaned star is a puzzle piece, revealing how clusters evolve through violence. Some ejections might even seed future star formation, as runaway stars plunge into gas clouds and trigger collapses like cosmic dominoes. Others, flung into the abyss, will drift forever, silent witnesses to the chaos that reigns in the crowded hearts of star clusters. Their very existence proves that for some stars, survival doesn't mean staying put, it means getting thrown into the dark and learning to shine alone. Gravity isn't just a force, it's the universe's ultimate illusionist, and nowhere does it perform stranger tricks than in the heart of dense star clusters. These cosmic crowds don't just warp space, they twist light itself, bending rays from distant objects into funhouse mirror distortions that reveal secrets no telescope could spot directly. When astronomers first noticed stretched-out galaxies and smeared quasar images behind clusters like Abell 1689, they weren't just seeing optical oddities, they'd stumbled upon nature's most precise scale, measuring invisible mass with the bending of starlight. The most dramatic examples look like celestial mirages. In the cluster SDSSJ 1095 plus 4623, a single background galaxy appears as 5 separate arcs, an Einstein cross, where the cluster's gravity splits light like a prism. Each distorted image tells a story. By analyzing their arrangement, researchers calculated the cluster's total mass is 50 times greater than its visible stars suggest, exposing vast halos of dark matter that would otherwise stay hidden. Other lenses, like those in the massive cluster MAX J0717.5 plus 3745, create grotesque cosmic smears, spiral galaxies stretched into glowing noodles wrapping around the cluster's core like strands of luminous taffy. But lensing isn't just about spectacular visuals. Subtler distortions betray even stranger phenomena. When Hubble studied the globular cluster M22, it spotted pinprick shifts in star positions, changes so minute they required comparing photos taken 18 years apart. These microlensing events revealed a shocking truth. The cluster is infested with rogue planets floating freely between stars. Each tiny flash marked a moment when one of these invisible worlds briefly magnified a background star's light, exposing planets we'd never see otherwise. The real power of these gravitational lenses lies in their precision. Unlike human-made telescopes limited by mirror size, nature's lenses scale with mass. The cluster Abell 380, for instance, acts like a lens 3 million light-years wide, a cosmic magnifier so powerful it lets us spy on galaxies from when the universe was barely 1 billion years old. Recently, this effect unveiled something even more profound. Galaxies so young they're still forming first stars, their faint light amplified 100-fold by intervening clusters. Without these natural telescopes, we'd be blind to the universe's toddler years. What makes star cluster lenses truly bizarre is how they warp time. Light from multiply imaged objects takes different paths around the cluster, arriving at slightly different times. In one famous case, the Hamilton object behind cluster Abell 370, the same supernova appeared twice, its light split into images arriving 45 days apart. This cosmic delay lets astronomers map the cluster's mass distribution in 3D, as if the universe itself provided the blueprints. Perhaps the most startling discovery is that some lenses appear stronger than they should be. The cluster El Gordo's lensing effect suggests 50% more mass than standard cosmology predicts, a discrepancy that might hint at dark matter behaving differently in these extreme environments. Other clusters show lensing patterns that suggest their dark matter is clumpier than models allow, as if unseen forces are sculpting it into shapes we don't yet understand. Every distorted image, every stretched galaxy, is a clue to the universe's hidden architecture. These light-bending clusters aren't just curiosities, they are forensic tools, revealing the fingerprints of dark matter, the distribution of rogue planets, and even flaws in our cosmic models. As telescopes grow sharper, who knows what other secrets will come into focus through nature's most powerful lenses? One thing's certain: when it comes to unraveling the universe's mysteries, sometimes you have to look at things sideways, literally. Some star clusters don't blaze with heat, they whisper in the cold. scattered across the cosmos are enigmatic gatherings of stars that radiate far less warmth than physics predicts, as if someone turned down the universe's thermostat. Take the cluster NGC 6709, where the red giants glow dimmer than they should, their surfaces barely reaching 3,000 degrees, a cosmic chill that leaves astronomers scratching their heads. These aren't just slightly cool stars, they're celestial anomalies operating by rules we haven't written yet. What could siphon away a star's heat so dramatically? One possibility lies in an unseen accomplice: dark matter. If certain clusters harbor dense pockets of this mysterious substance, its gravitational influence might alter how heat circulates within stars, acting like an invisible heat sink. Imagine a bonfire struggling to stay lit in a freezer. Stellar cores in these clusters could be fighting a similar battle, their nuclear fires dampened by forces we can't directly observe. Supporting this theory are odd velocity measurements in clusters like Palomar 14, where stars move more sluggishly than their combined mass should allow, hinting at dark matter's ghostly drag. But dark matter isn't the only suspect. Some clusters might host failed stars, brown dwarfs lurking undetected among their brighter siblings. These cosmic misfits, too massive to be planets but too small to ignite full fusion, would leach infrared radiation from their surroundings, creating localized cold spots. Infrared telescopes have spotted hints of this in the Hyades cluster, where mysterious gaps in the thermal map align with where rogue brown dwarfs might drift, invisible to optical scopes but casting a detectable chill. The plot thickens when you examine stellar chemistry. In the unusually cool globular cluster M72, certain stars show bizarrely low helium levels, an element normally abundant in aging stars. This deficit suggests something is disrupting convection, preventing heat from rising to the surface efficiently. One controversial explanation proposes quantum processes at play. Ultra-dense particles called actions, theorized components of dark matter, could be forming inside these stars and carrying heat away like microscopic thieves. While still speculative, action cooling would explain why some clusters act like cosmic refrigerators while others burn normally. Perhaps the most unsettling cold clusters are those with no stars at all. Radio telescopes have detected faint, sprawling structures like the Dark Ridge near the antennae galaxy's regions, emitting only microwave radiation at temperatures barely above absolute zero. These might be clusters that formed from gas too tenuous to ignite stars, their gravitational bonds maintained by something other than stellar heat. Or they could be remnants of clusters stripped bare by tidal forces, leaving behind only their darkest members, black holes and neutron stars orbiting in frigid silence. The implications ripple beyond astrophysics. If cold clusters exist because of novel particles or dark matter dynamics, studying them could unlock secrets about the universe's most elusive components. They might even serve as natural laboratories for quantum gravity, where extreme conditions warp space-time in ways no earthbound experiment can replicate. Every anomalous temperature reading, every dimmer than expected star, is a clue waiting to be deciphered, a reminder that the universe doesn't just challenge our expectations. Sometimes it quietly defies them, leaving us to trace the cold trails of its quietest rebellions. Tucked away in the quiet corners of star clusters like M4 and NGC 6397, astronomers have uncovered celestial time travelers, stars so ancient they carry the unspoiled chemistry of the universe's infancy. These aren't just old stars, they're cosmic vaults safeguarding hydrogen and helium nearly untouched by the polluting explosions of later stellar generations. Their atmospheres are like pages from a 13-billion-year-old diary, written in elements forged minutes after the Big Bang. What makes these stars so extraordinary is their purity. Most stars in the universe, even ancient ones, bear traces of heavier elements like carbon or iron, debris scattered by exploding supernova. but a rare few, like the star known as 2 Mass J 18082 plus 44264, show almost no contamination. Their spectra reveal hydrogen lines sharper and clearer than in any other stars, as if their gas had never been stirred by the violent deaths of neighboring suns. Finding them is like discovering a sealed cave deep in a modern city, its walls untouched by centuries of progress outside. The hunt for these relics hinges on their subtle chemical fingerprints. In the globular cluster NGC 6838, researchers spotted a star with lithium levels 100 times lower than expected, a telltale sign it formed before this fragile element could be destroyed by nuclear fusion. Another, in the cluster M92, lacks even a whisper of strontium or barium, elements typically sprinkled into star-forming gas by the first supernova. These absences are clues, painting a picture of a time before the universe learned to forge complexity. But preserving such pristine material requires cosmic luck. These stars had to form early, in isolated pockets of gas shielded from the polluting winds of exploding giants. Simulations suggest they might be survivors of dwarf galaxies devoured by clusters long ago, their purity preserved like insects in amber during the violent merger. Others could have been born in the outermost fringes of clusters, where infalling gas remained unpolluted by the chemical factories at the core. Their very existence hints at a time when star formation wasn't uniform, but patchwork, a universe where some regions leaped ahead into the era of heavy elements while others lingered in primordial simplicity. The real magic lies in what these stars reveal about cosmic dawn. Their oxygen-to-hydrogen ratios, for instance, are 1,000 times lower than the Sun's, matching predictions of how the first supernova enriched the cosmos. Some even show odd nitrogen enhancements, potential evidence of the universe's very first stars, which may have burned at temperatures and pressures so extreme they produced exotic nuclear byproducts. By studying these patterns, astronomers can reconstruct the life cycle of those long-vanished pioneers, stars hundreds of times more massive than our Sun that lived fast, died young, and seeded the universe with its first heavy elements. Yet these time capsules aren't just about the past, they're testing grounds for fundamental physics. The primordial lithium levels in some stars conflict with predictions from Big Bang nucleosynthesis, hinting at gaps in our understanding of the early universe's particle interactions. Others show puzzlingly low beryllium, suggesting cosmic rays in the infant universe behaved differently than today. Every deviation from expectation is a breadcrumb leading us toward answers, or deeper questions about how the cosmos assembled itself from simplicity to complexity. And the search isn't over. New telescopes like the James Webb Space Telescope are probing even older clusters, searching for stars that might predate the first supernova entirely. Finding one would be like uncovering a fossil from before the Cambrian explosion, a glimpse into a universe still learning how to build itself. These stars remind us that the cosmos has a long memory, and if we know where to look, it's willing to share its oldest secrets. Some star clusters shine with a brilliance that defies logic, their combined starlight adding up to far more than the sum of their parts. Take the Phoenix cluster, a glowing behemoth in the distant cosmos that outshines entire galaxies, radiating with the intensity of trillions of suns. Yet when astronomers tallied its stars, the numbers fell woefully short. Even accounting for supermassive black holes and swirling nebulae, nearly half of the light has no identifiable source, as if the cluster is hiding a cosmic light switch we haven't found yet. The leading explanation dances at the edge of physics: dark matter annihilation. If dark matter consists of weakly interacting massive particles, or WIMP, their collisions could theoretically release energy as gamma rays and visible light. The Phoenix cluster's extreme density might be the perfect environment for these rare interactions, with invisible particles smashing together like ghostly fireflies lighting up the void. Supporting this idea are faint, unexplained halos of ultraviolet light detected around similar clusters, radiation that conventional astrophysics struggles to explain without invoking exotic processes. Yet not all clusters fit this mold. In the Coma cluster, X-ray telescopes caught streams of superheated gas glowing far brighter than the stars alone could produce. Here, the culprit might be more mundane but equally fascinating: intergalactic gas compressed to millions of degrees by the cluster's gravity, emitting light as it cools. Imagine a cosmic forge where the sheer weight of the cluster's mass squeezes gas until it glows white-hot. Even so, models suggest this mechanism can't account for all the excess brilliance, leaving room for even wilder possibilities. Then there's the measurement problem. Some overbright clusters might be illusions caused by gravitational lensing, their immense mass bending light from background galaxies and quasars, amplifying their apparent glow. The cluster Abell 521, for instance, was initially flagged as anomalously luminous until researchers realized its light was being boosted by a perfect alignment with an even more distant quasar. The universe, it seems, enjoys playing tricks with perspective, but the most tantalizing cases resist all conventional explanations. The cluster El Gordo emits high-energy radiation that aligns with no known particle interactions, sparking speculation about decaying dark matter or even primordial black holes evaporating in bursts of Hawking radiation. Each unexplained photon is a breadcrumb hinting at physics beyond the standard model, clues that these clusters might not just be bright, but broadcasting secrets about the universe's hidden architecture. The search for answers is far from over. New observatories like the upcoming Nancy Grace Roman Space Telescope aim to map these anomalies in unprecedented detail, separating true excess light from cosmic illusions. Whether the solution lies in exotic particles, unseen dynamics, or something entirely unexpected, one thing is clear: when a star cluster shines too bright, it's not just showing off, it's inviting us to look closer, to question deeper, and to rethink what we know about the dark and luminous fabric of the cosmos. From pulsars devouring their companions to stars that cheat death, from invisible dark clusters to runaway hypervelocity stars, we've traveled through a cosmic gallery of the universe's strangest creations, all hidden within star clusters. These glittering stellar cities aren't just pretty ornaments in the night sky. They're laboratories where the laws of physics twist into something extraordinary. Think about it: blue stragglers burning with stolen youth, diamond planets orbiting stellar corpses, and zombie stars that refuse to fade. Each discovery peels back another layer of the universe's rulebook, proving that what we think we know is just the beginning. Consider how these findings reshape astronomy. The missing red giants force us to question whether dark matter is quietly pulling strings in these clusters. The phantom X-ray sources hint at particles or objects we've yet to name, and the ancient chemically pure stars, their time machines offering snapshots of the universe's first breaths. Even something as seemingly simple as a star cluster's motion, like those caught in the dark flow toward the great attractor, reveals how much of the cosmos remains unmapped, its largest structures lurking just beyond our sight. But here's the thrilling part: for every mystery solved, a dozen more emerge. What if dark stars powered by dark matter annihilation are hiding in plain sight? Could some globular clusters actually be the remnants of devoured galaxies, their true origins written in orbits we've yet to decode? And what about those reborn clusters where second generations of stars ignite from the ashes of the first? The more we learn, the clearer it becomes. Star clusters aren't just relics of the past. They're alive, dynamic, and teeming with secrets waiting to crack open the next frontier of cosmic understanding. So we'll leave you with this: if star clusters can rewrite the rules of stellar life and death, bend light like cosmic lenses, and hide entire populations of invisible black holes, what else might they be capable of? The universe loves a good plot twist, and if history's any guide, the next revelation will be stranger than anything we've covered today. Now it's your turn. Which of these discoveries left you in awe? Drop your favorite in the comments because the conversation about these celestial enigmas is just getting started.